Good morning, ladies and gentlemen. Uncle Lee here. You figure out for yourself who Cisco Kid was. A little history lesson there, a little history lesson here. History of the alternating series test. Let's talk about this test to see if an alternating series converges or not. So let's given this, here's the test. Given I have this alternating series from n equals 1 infinity to negative 1 n plus 1 a sub n. Here are my terms. A sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus dot dot dot. That's my series. If the following three conditions hold, we have to be careful with these following three conditions. Each a sub n is positive. So what I want to do is I'm going to grab each of those and I want to verify that each term there is positive without the positive and negatives there, without the plus and minuses. Each term has to be positive. We'll look at that. More importantly, well, as important, because all three of these conditions have to hold, for some n, for some integer, there has to be an n greater than or equal to that integer where the terms begin to decrease, or the next term is smaller than the previous term, smaller than or equal to the previous term. The terms must decrease. Those positive terms must decrease. If the absolute values of the terms decrease, that's the second condition. Not only do they have to decrease, but the terms, as n goes to infinity, must go to 0. So they have to decrease, and they have to decrease to 0. So the absolute, I've seen this in other books where they just say, hey, the absolute value of the terms decrease to 0, provided the terms are positive of this alternating series. If all three of these conditions hold, if A and B and C, if they hold, then we say that this alternating series converges. Let's do an example. We're going to start off here with a rather simple example. Here I have an alternating series. Series from n equals 2 to infinity of negative 1 n plus 1 over ln of n. Well, let's see if the three, it is alternating. But, it's a good idea to verify that it is indeed alternating. And if I have n greater than 2, then I know ln of n is going to be a positive. Sometimes ln is negative if n is less than 1. And that's why we're starting at 2. I can't start at 1. If I start at 1, then I have something that's undefined. So this guy is alternating. And so now I'm just going to verify that each term, it's going to start off positive and then go negative. But each term, if n is greater than 2, then I know that ln of n is greater than 0. Therefore, 1 over ln of n is going to be greater than 0 also. So A, condition 1 holds. All of my terms are going to be positive. Good deal. Let's check the next. Are the terms, is there some n where those terms begin to decrease? Not only do those terms decrease, do they decrease to 0? Let's see. Well, if n is greater than 2, I know that ln of n is less than ln of n plus 1. ln is an increasing function. It increases slow, but it is increasing. And so therefore, if it is increasing, then 1 over ln of n certainly is greater than or equal to 1 over ln to n plus 1. So this particular guy is decreasing. If this is decreasing wherever n is greater than 2, my terms are decreasing. The next term is smaller than the previous term. Condition B holds. Not only does condition B hold, but the limit as n goes to infinity also of a sub n, of 1 over L sub n, that goes to 0, because we saw that we know that ln increases, so it increases slow, but 1 over something that's going to get eventually big, huge, is going to go to 0, so therefore C holds. So I have condition A holding, B holding, and C holding. Therefore, I can say that this alternating series from n equals 2 to infinity of negative 1 and n plus 1 over L and n, this guy converges by the alternating series test. Example 2. Oh, example 2. Oh, example 2. Nice, nice, nice. This guy looks oddly familiar. The series from n equals 1 to infinity of negative 1 to the n minus 1 over n. I wrote out some terms so that you could recognize this particular series. 1 minus 1/2 plus 1/3 minus 1/4. This is the very popular alternating harmonic series. The very popular alternating harmonic series. Let's see if this guy converges. What is your gut feeling? Do you think this converges? Well, if you remember not long ago, on a previous video, we looked at the infamous harmonic series. Now we're looking at the famous or popular alternating harmonic series. So let's see if the conditions hold. Condition A, if n is greater than 1, 1 over n clearly is greater than 0, so condition A holds. Okay, and now do my terms decrease? Well, if n is greater than or equal to 1, then n is certainly less than n plus 1. Therefore, 1 over n is greater than 1 over n plus 1. So then my terms do decrease. My terms do decrease. Clearly, if my denominators remain the same, my numerators remain the same, my denominators are going to get bigger, then this next term is going to be smaller, clearly. So the terms decrease. Nice. That's the value of the terms decrease. And clearly, the limit as n goes to infinity, 1 over n is equal to 0. Nice. So all three of the conditions of the alternating series test holds. Therefore, I can say, what can I say? Wow, the result. The series n equals 1 to infinity, negative 1 to n minus 1 and 1 over n converges. That famous, popular alternating harmonic series converges. Interesting. That is interesting when you think about this dude right here. Let's think about that rascal. Oh, that guy right there. What about that dude? The alternating series. This is the famous divergent harmonic series. It clearly is divergent. We could say it's divergent by the P-series test. So what does that, oh boy, so I've got this guy that diverges, and I got the alternating harmonic that converges. What can I say about this? Well, this is going to be a really nice example of a special series. And if I recall the theorem, I'm not quite sure what video we introduced this theorem. I think it was the P-series video. I'm not quite sure. But here was the theorem. If I have the series of absolute value of the terms, if this guy converges, if the series of the absolute values converges, then that series converges. And not only converges, we would say that A sub n, we would say that that series converges absolutely. So if the absolute values of a series converge, then that series converges. Not only does it converge, we say that that particular series converges absolutely. And in calculus, many times, and I spoke to this when I first introduced this theorem, we have to be careful of the hypothesis and the result of the theorem. If, then, hypothesis holds, then this is true. The converse of that necessarily isn't true, as we just verified with the alternating harmonic. Because what do we have here? We have, what do we have if I take the absolute value of the alternating harmonic series? That's the harmonic series, which I know diverges. So this does not imply that. So I certainly can't say that the absolute values of the harmonic series converges, because it doesn't. So what do we say? So we say that the alternate harmonic series that we showed in the previous slide was convergent, we say that this particular series converges conditionally. That's a nice example of what it means to converge conditionally. So we have absolute convergence, and now we have converge conditionally. Okay? Let's go to another example. Another, a little bit harder example of alternating series. Keep in mind where we are. That's what this video is about. This video is about determining whether alternating series test whether an alternating series converges. If all three of these conditions hold, bam, 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 then we know the series converges. Let's look at it. A more difficult series. Let's look at, not that one's too easy, that one's too easy. Let's jump down here to, where is that rascal at? Oh, golly gee, this one right here. Here's a nice one. This is a nice series right here. So this is the series that I'm looking at, the alternating series. M equals 1 to infinity of negative 1 to the n plus 1 of 1 plus n over n squared. Does that series, it's alternating, n is greater than 1, all this stuff here is positive, so it's going to alternate between negative and positive, negative and positive. Let's see if this series converges. Well, step number 1, let's see if A holds. Let's see if each term is positive. And I think it's pretty clear that if n is greater than or equal to 1, I'm talking about n is greater than 1. 1 plus n is going to be greater than 0. Hello. N squared is always greater than 0. So therefore, 1 plus n, well, if n is greater than 1, n squared is greater than 0. But 1 plus n over n squared, that's going to be positive. So condition A holds. Condition A holds. Let's look at condition B. Now condition B, what do I want? Ooh, golly gee. What I want now is, I want, for some n, I want these terms to decrease. I want the n plus 1 term, this is the nth term, I want the n plus 1 term to be smaller than the nth term. I want the n plus 1 term to be smaller. So what, and that's going to be difficult. That's not so easy to determine right there. Keep in mind, this is going to be n plus 2 over n plus 1 squared, so I want this to happen right here. The n plus 1 term, I want it to be smaller than the nth term. And what I want is keep in mind from the very first discussion, I want the terms to decrease, those positive terms to decrease. Not only do I want them to decrease, I want them to decrease to 0. So I haven't verified B yet. I don't know that this is true. And that's not intuitive. You just can't look at that and say, oh yeah, oh yeah. That's not when you, oh yeah. Let's hold your horses for a minute. So, but let's check to see if those terms do go to 0, because they could go to 0 and not be completely decreasing. So, and this is certainly true. The limit as n goes to infinity, 1 plus n over n squared. That's going to look like way out there as n goes to infinity. As n goes to infinity, sorry for the notation there. It's going to look like 1 over n, which goes to 0. Bam. So check. So condition C is checked off. Condition A is checked off. But we still need to check condition B. And how do we determine if something decreases? Can you think about how you would determine if a function decreases? So keep in mind, a sequence is a function. I want to know that this thing decreases. Well, so how do you determine? If you go back a long way back, what would you do? Oh yeah. What I could do, this is the sequence that I want to decrease when n is greater than 1. I could look at this function and check out what? Yes, you're correct. Check the derivative of that function. So let's find the derivative of this quotient function. It's fairly easy. It's a very simple quotient to determine. Okay, so I've got the f divided by g, f prime, g, f prime g. One derivative of that is 1 times x squared minus g prime f. So I got x squared minus 2x times 1 plus x. 2x times 1 plus x is going to be what? 2x plus 2x squared. And I'm going to subtract that, so it's going to be x squared minus 2x squared. X squared minus 2x squared is going to be 1 negative x squared. And so now I have negative x squared minus 2x. I can factor that negative out. And so here's my derivative. Negative x squared plus 2x over x to the fourth, g squared, the bottom square, quotient rule. You can review the quotient rule if you like. We definitely should have our head completely wrapped around the quotient rule. So what do I know here? Well, if x is greater than 0, if x is greater than 0, and keep in mind, the sequence that I was talking about, n was greater than 0, I know that this guy is going to be positive. I know that that guy is going to be positive. I know that that guy certainly is going to be positive. So then the negative of all that is going to be less than 0. The negative of positive is going to be less than 0. That's nice. What does that tell me? That tells me that f of x decreases when x is greater than 1. So if this f of x decreases when x is greater than 1, this guy here is also going to decrease, and therefore condition B holds. There are some of the more elaborate alternating series problems where you have to find that derivative and verify that those terms do indeed increase. And we verify that by looking at the derivative. Derivative negative implies the function is decreasing. So there. So all three of the conditions hold. So this particular series does decrease, does converge, because I have verified all three of the condition A, B, and C. So here's very simple. Here's our last example for this video, a very simple one. Alternating series. Clearly alternating series. If n is 1 and n is greater than 1, all this stuff is positive. But look, I jump down here and I can recognize that right away that the nth term as n goes to infinity goes to 3/4, which doesn't go to 0. So all three of the conditions, no way all three of the conditions. So this particular alternating series diverges. So there you have it. A little video on the alternating series test. Very important video. So thanks for showing up. I will see you later.